Welcome back to this course, Advanced Memory Hierarchy Design. The topic of this and the next two lessons is prefetching, a technique in which code or data is fetched into the cache before it is used. Prefetching can be implemented in software or in hardware. The main topic of this lesson is software prefetching, and in the next two lessons I will focus on hardware prefetching. This lesson is based on section 2.2 of the textbook by Hennessy and Patterson. It is also based on the article Data Prefetch Mechanism by Stefan van der Wiel and David Lilja, which appeared in ACM Computing Surveys in June 2000. The topic of this lesson is prefetching. When prefetching is employed, we speculate on future instruction and data accesses and fetch them into cache before they are needed. It is also possible to prefetch into a register, but in this lesson I will focus on cache prefetching. Prefetching attempts to reduce the miss rate if the prefetch was issued on time, or the miss penalty if the prefetch was too late. In general, it is easier to predict instruction accesses than it is to predict data accesses, since instructions are usually accessed sequentially, interrupted only by branches, while the data stream is usually not sequential, since different loads typically access different data structures. Generally, there are two different types of prefetching: software prefetching and hardware prefetching. Software prefetching uses explicit prefetch instructions that need to be inserted into the code and are the topic of this lesson. Hardware prefetching uses a hardware mechanism that predicts the code or data that will be needed in the future and issues the corresponding prefetches. I will first discuss software prefetching, and in the next lesson I will discuss hardware prefetching. Prefetching has several aspects. The first is accuracy, defined as the number of useful prefetches divided by the total number of prefetches. A useful prefetch is one that fetches code or data that is used later and not unused. The second aspect is coverage, defined as the number of useful prefetches divided by the number of cache misses when prefetching is turned off. A prefetcher can have a high accuracy by not deciding to prefetch unless it is absolutely certain, but then it will have a low coverage. The third aspect is timeliness. Prefetches should be issued not too late and not too early. When it is issued too early, the new data might replace useful data that is still going to be used. This is called cache pollution, since the new data pollutes the cache. If a prefetch is issued too late, the code or data may not yet be present in cache when it is needed, and so the CPU has to stall waiting for the data to arrive. Such stall cycles are called hit-wait cycles. On this slide, I want to illustrate the aspect of timeliness. When we have no prefetching and a blocking cache, then the timing might look like this. The CPU computes for a while and then it incurs a miss M1, then it stalls until the block is fetched, and then it continues with the fetched data and again computes for a while, and then it incurs another miss M2, and so on. When we have perfect prefetching, the prefetches are issued exactly on time, as illustrated in this timing diagram. The prefetches, indicated by the dark blue color, are issued exactly memory latency cycles before they are used. So when the CPU accesses the prefetched data, it will hit in the cache as indicated by the green colors. Finally, this timing diagram illustrates degraded prefetching. The first prefetch is issued just before the access to that data, so the CPU still has to stall for a large number of cycles before the data arrives and can be used. The second prefetch is issued a bit longer before its actual use, here indicated by M2, but still the CPU has to stall for a large number of hit-wait cycles. Finally, the third prefetch is issued too early. The data is present in the cache long before it is used here and might have replaced other data that is still needed. I will now discuss software prefetching techniques. In software prefetching, there are explicit prefetch instructions that prefetch data into the cache. These instructions are either manually coded by the programmer or inserted automatically by the compiler. Software prefetching implies that additional prefetch instructions need to be executed, and this overhead should of course not be larger than the benefits of prefetching. The biggest challenge of software prefetching is the placement of the prefetching relative to the load or store that uses the prefetched data. As said before, it should not be too late, but also not too early. I will focus on loop-based prefetching, prefetching inside loops. Loop-based prefetching is common in scientific codes, and scientific codes often also suffer from poor cache utilization. Furthermore, the array referencing pattern is often predictable. The address of the data that is needed in a few iterations from now is equal to the current address plus a constant stride. Then the prefetch instruction need to be placed inside the loop body such that the current iteration prefetches data for a future iteration. This shows the dot product kernel again without prefetching. In the current and the next examples, I assume that each cache block can contain 4 elements. Then this kernel will incur 2 misses per 4 iterations, a miss for the first access to element of A in a block and a miss for the access to the first element of B in a block. The second, third and fourth element of A as well as B in a block will hit the cache. Now we add prefetching instructions to the code. This code illustrates naive prefetching. In the iteration that accesses AI and BI, we prefetch AI plus 1 and BI plus 1. For several reasons, this code is naive. First, the overhead is obviously too high, since it issues unnecessary prefetch operations. We only have to issue 1 prefetch per cache block rather than 1 prefetch per element. Second, the code might generate an exception on the last iterations, since elements AN and BN do not exist. So this is definitely not the way to go. Here's again the dot product kernel without prefetching. And here I show the code with prefetching that tries to solve the problems identified on the previous slide, but again in a naive way. The code version might be called naive prefetching with predicate. Now in every iteration there's a predicate that tests if the data to prefetch is within array bounds and if I plus 1 is a multiple of 4. If both conditions are fulfilled, the prefetch is executed, otherwise no prefetch is issued. Obviously, the overhead is still too high. Performing these tests likely takes more time than the potential benefits of prefetching. It is better to unroll the loop, as we have also done several lessons ago. This shows the prefetching code with loop unrolling. The unrolling factor is equal to the block size in elements, which I assume to be 4. Every loop iteration prefetches the next blocks of A and B and then accesses the elements I plus 1, I plus 2 and I plus 3. This code hopefully eliminates most cache misses and unnecessary prefetches. 2 problems still remain, however. These problems occur in the first and last iteration. Because the data has not been prefetched, there will be cache misses in the first iteration. In addition, there will be unnecessary and perhaps illegal prefetches in the last iteration. To solve these problems, we should modify the code in a way that is similar to software pipeline. I will do so on the next slide. This shows the prefetching code with software pipelining. First, we prefetch the scalar value .p, the first block of A and the first block of B. Then there is an unrolled loop that is identical to the code on the previous slide, except that the upper bound has been replaced by n-4 as highlighted in red. This ensures that no unnecessary prefetches will be generated. Finally, there is another loop that processes the remaining elements of A and B. This code covers all loop references, meaning that each access or reference is preceded by a matching prefetch. In this, as well as the previous code versions, I assumed, however, that prefetching one iteration ahead is sufficient to hide the memory latency. In general, it may be necessary to prefetch L over S iterations ahead, where L is the average memory latency and S is the shortest execution time of one iteration, including the overhead. This makes a nice exercise. Show the code when L over S equals 4. Software prefetching has a number of limitations, however. First, it is restricted to loops with predictable array accesses, and it is very hard, if not impossible, for applications with irregular access patterns such as searching in a tree-based data structure. Second, software prefetching may lead to a significant code expansion. Not only will there be execution overhead to execute the prefetch instructions, the additional instructions and loop unrolling may also increase the instruction cache miss rate. Third, it must be performed by the compiler in a static way, meaning that the compiler cannot exploit runtime information, or, what is even worse, it must be performed manually in the code by the programmer, which of course reduces programmer productivity. This completes this lesson. Thanks for watching. In the next 2 lessons I will discuss hardware prefetching. Hardware prefetching uses a hardware mechanism to predict which blocks will be needed in the future and issues the corresponding prefetches. Stay tuned.